Good evening, students. So in today class we'll discuss the last topic of module 5, steam nozzle. So the topic name is condition for maximum discharge through an isentropic nozzle. So this topic has many times appeared in the VTU question papers. So the question may be like this: derive an expression for condition for maximum discharge through an isentropic nozzle. So if you refer in from previous question for June July 2018, the question is asked in different way. Prove that P2 by P1 is equal to 2 by n plus 1 to the power of n by n minus 1. So here n is index of expansion. So why he used the word index of expansion in the question paper is, so we know already studied in the previous topics, previous classes, that when the fluid or steam flowing through the nozzle, expansion takes place. So what type of expansion it is? It is a reversible adiabatic expansion process, that is isentropic process. So there is a reason here in the question paper he used the word isentropic process. And reversible adiabatic process follows the law PV to the power of n is equal to constant. We studied in module number 1 and we studied in the thermodynamics previous semester. So polytropic process PV to the power of n is equal to constant. So we will use the knowledge of thermodynamics what we studied in the previous semester. So this question is asked many question papers. This December 2019-20, subject code 17ME43 and question number 10A. So here I have shown only 3 question papers, latest question papers, but this topic is very important for exam point of view. So before that, in some question papers he has asked for 2 marks critical pressure ratio. So we will write the answer for that. Critical pressure ratio is defined as the ratio of pressure at the throat or pressure at the exit of the nozzle, that is P2, to the pressure at inlet of the nozzle. How will you define? Critical pressure ratio is defined as the ratio of pressure at exit of the nozzle and to the pressure at inlet of the nozzle. So that is P2 by P1. So is equal to 2 by n plus 1 to the power of n by n minus 1. So we will discuss one step by step. So before going to the next step, first we will understand the definition of discharge. So what is discharge? Discharge is a volume flow rate of fluid or volume flow rate of water or any fluid, that is steam, gas, whatever may be. So that discharge will be represented by a letter Q. Here we have written discharge Q is equal to area into velocity. So this formula, this equation you might have studied in fluid mechanics subject in the fluid dynamics chapter. Okay, so Q is equal to area A, velocity is V. Unit of area is meter square, velocity unit is meter per second. So if you multiply these two quantities, you will get meter cube per second. Meter cube per second is a unit of discharge. In the numericals he may ask you to calculate discharge through the nozzle. So unit is important. So you remember unit of discharge is meter cube per second. So if you are writing the discharge equation at inlet of the nozzle here, then area at inlet of the nozzle, that is A1, and V1 is a velocity at inlet of the nozzle. So A1 is cross sectional area, so he may give the diameter of the nozzle at the inlet. So using A1 is equal to pi by 4 d square, you will calculate A1 and multiply by V1, you will get the discharge. Similarly, the discharge at Q2 is equal to AT into V2, and these two equations we can call it as continuity equation. So condition is density of the fluid is same. At inlet the density is same as at outlet. For example, if you are considering water at inlet and water, density of water is 1000 at the inlet and at the same time the density of water at outlet of the nozzle is also 1000. So this become Q is equal to A1 V1 A2 V2. This is called continuity equation. And to move further, one more point you need to remember is mass flow rate, that is law of conservation of mass. So what is it? Law of conservation of mass is the total mass of steam entering or passing to the nozzle is equal to total mass of steam which is coming outside. M1 is equal to M2, or if you are defining with respect to time, M1 dot is equal to M2 dot. Okay, so these are the two important points you remember for deriving this equation. So now consider one convergent nozzle. So I have taken one convergent nozzle here. The convergent nozzle is insulated throughout. So when you insulated, it is understood that heat exchange between the system and the surrounding is 0. So on the both the side we have taken Q is equal to 0. And dear students, don't become confused with this Q and this discharge Q. This is volume flow rate of steam, unit is meter cube per second. This is heat transfer rate, that is we have taken it as, assume it as 0. Okay, so next point. So at inlet of the nozzle always the pressure is more. So this high pressure steam when enters into the nozzle and flows through the nozzle, this high pressure will be converted into high velocity. So at the exit of the nozzle at point number 2 or section 2, the velocity will be much greater than inlet velocity. So that is the reason we have written here. So V2 is much greater than V1. So V2 and V1 are velocity terms. And when high pressure is converted into low pressure, so value of P2 at section 2 is less than P1. Okay, so these are the some terms we have taken. M1 dot is equal to mass flow rate of steam at inlet. What is the unit of mass flow rate? Kg per second. Here we have done the unit. Similarly, I have taken A1. What is A1? A1 is area of cross sectional of nozzle at inlet, that is meter square. Similarly, V1 velocity at steam at inlet. And dear students, here I have taken velocity in place of V1, I have taken C1, because here one more time I will get specific volume. One more property of the steam I need to discuss here, that is specific volume. The specific volume will be represented with V1. Okay, so to avoid the confusion between this V and this V, we have taken velocity as C1. So similarly, P1 is a pressure of steam at inlet. Okay, so H1 is enthalpy of steam at inlet. The unit of enthalpy is, already we know it, kilojoule per kg. Okay. Similarly, as I told you now, V1, the small v I have taken, it is represented with specific volume of steam at inlet, or volume of 1 kg of steam, that is specific volume. So now similarly, these properties I have taken at outlet. Here I have written M2, A2, V2, P2 and H2 are corresponding points at section number 2, that is outlet. Dear students, don't become confused again. Clearly I have written here, V stands for specific volume. In some books, in some question paper itself, he will give velocity V, or he may use the velocity in different letters, that is C. So both are same. Okay, now so M1 dot is equal to M2 dot. This is one form of continuity equation we have written here. And one thing you need to remember here, mass flow rate M1 dot is not same as the discharge. Both are different. Some students will be thinking that mass flow rate and discharge both are same. Both are not same. Okay, if it is same, the unit could have been kg per second. The unit of mass flow rate M is kg per second, but discharge unit is meter cube per second, that is volume flow rate, this is mass flow rate. So please remember that point. So now I need an expression for mass flow rate. So I have taken m is equal to, so how the area into velocity divided by specific volume. How this equation is arrived here is, so for that I have shown here density is equal to mass by volume. This is the basic fundamental formula of density. So I need mass, so take left hand side, so density into volume, divide both side by time. So mass by time is m dot, mass flow rate with respect to time. So density rho as it is, so volume divided by time I have written as it is. So unit of mass kg, time unit is second, density I have written as it is. So volume unit is meter cube, time unit is second. So here if you split meter cube into two parameters, meter square into meter, meter square is the unit of area, and meter per second is the unit of velocity here. So area into velocity divided by, I have taken specific volume. The reason is, so 1 by specific volume or reciprocal of specific volume is called density. Density is also reciprocal of density, or density is mass by volume, both are same. So here m dot is equal to area, velocity, as I told you I will use the letter C to avoid the confusion in the equations. So specific volume is V. So m dot is equal to area into C into V. The same equation I have taken here. M is equal to area into velocity divided by specific volume. So this is the equation I am writing at exit of the nozzle, because at the inlet of the nozzle the velocity C1 and pressure P1 are known values. We don't know the velocity at exit of the nozzle, and similarly we don't know the pressure at exit of the nozzle. So continuity equation, m2 same, I have written a2, velocity at exit of the nozzle C2, specific volume at exit of the nozzle V2. This equation I have taken it as 1. So once I calculate the equation or value of m2, I will multiply or with velocity I will get the discharge. You can ask a question that, sir, in the previous lecture we have derived expression for velocity at exit of the nozzle, that is C2. C2 is equal to square root of 2000 into h1 minus h2. So you substitute here and multiply with the area of the nozzle at exit, you can calculate easily m dot 2. Dear students, it is not like that. Here velocity C2, I have written the expression here, C2 or velocity at exit of the nozzle 2 is a function of enthalpy, but here we need an expression in terms of pressure, that is critical pressure ratio P2 by P1, and there should be one index of expansion n. Here there is no such terms, just parameters. Here clearly I have written this is in terms of enthalpy, so you cannot substitute the value of C2 directly here and calculate m2. Okay, so for that reason, so there are some important points are there we need to discuss. So first, to find velocity at C2, that is our aim, because A2 will be given by the designer, because A2 is a geometric parameter. Once you take the nozzle, diameter will be given, so A2 is equal to pi by 4 d2 square, you can calculate A2, and specific volume of V2, because density is there. If we give the density of the fluid at our outlet, density is equal to 1 by V2, we can calculate V2 is 1 by rho easily. So these two are unknowns, actually parameters to calculate m2. So next point, very important point here. So enthalpy drop in nozzle is h1 minus h2. Dear students, so I will go back to the diagram. This is h1 at inlet, h2 outlet. So h1 is the enthalpy at inlet, h1 minus h2. Initially enthalpy is more, high pressure, high enthalpy steam when passed through the nozzle, expansion takes place here, due to expansion the enthalpy of the steam decreases. So that decrease or drop of enthalpy, where it has gone? There is no chance of going outside because all surfaces boundary are insulated. So that decrease of enthalpy of the steam has increased kinetic energy. We know one fundamental principle of heat energy transfer: energy neither be created nor be destroyed, but one form of energy is converted into another form. Here that drop in enthalpy energy is converted into another form, that is kinetic energy. That is what definition of the nozzle says. Nozzle definition is: nozzle is a device which varying cross sectional area which decreases the pressure and increases the velocity. Decreases the pressure is nothing but decrease the enthalpy of the steam. So by decrease the enthalpy, the kinetic energy of the steam increases. So that energy equation I have written here, that here enthalpy drop in nozzle H1 minus H2 and is equal to gain in kinetic energy, because the enthalpy drop or pressure drop is converted into increase in velocity of the steam. So amount of energy which is dropped through the nozzle is equal to amount of kinetic energy gain, because initial kinetic energy is C1 square by 2. What is the formula for kinetic energy? Kinetic energy is equal to half mv square. Half is nothing but 1 by 2 I have taken here. M is for unit mass of steam, we are writing the expressions, so m will become 1. So half into 1 into C1 square, that is velocity square. But velocity C2, or you can take V2, at exit or outlet of the nozzle is much greater than inlet velocity, because at the inlet of the nozzle velocity will be too less but pressure will be too high. Okay, so too less so that we can neglect the velocity. And dear students, it is I have written it as 0, but mathematically I will take it as 0, but velocity will not be 0. Here instead of writing negligible, we will substitute the value of C1 as 0 only. Okay, so C1 is equal to velocity of approach or velocity at inlet of the nozzle. So substitute the value of C1 as 0. So here H1 minus H2 as it is, C2 square by 2. So C1 square by 2 I have substituted 0. So it is negligible. So I need the expression for C2, because in the equation number 1, m dot, that is mass flow rate, is depends on area, velocity at exit and specific volume of fluid at exit. So now first I will write the expression for C2. So C2 is equal to C2 square by 2 is equal to H1 minus H2. So next step I have taken C2 square by 2 as it is. And now, so this drop in enthalpy H1 minus H2 I have replaced with the new term n by n minus 1 into P1 V1 minus P2 V2. So you can ask how this equation is replaced with a new equation. And dear student, just remember the thermodynamics in the last semester thermodynamics what we discussed. What is the expression for work done for an adiabatic process? You have taken P1 V1 minus P2 V2 divided by n minus 1. Understood? That is reversible adiabatic process. We derived expression for isothermal, we derived expression for work done for polytropic. Similarly, for another 3-4 thermodynamic processes we derived. So hope you remembered it. So here I have written for your help PV to the power of n is equal to constant. So that is isentropic flow or reversible adiabatic process. So reversible adiabatic process, PV to the power of gamma is also equal to constant. If the value of gamma is 1.4, then we will apply that equation. But here we do know the value of gamma. So instead of gamma, we have taken n, polytropic index or polytropic expansion index. Both are same. PV to the power of n is equal to constant. If you solve this equation and if you write the expression for work done, you will get n by n minus 1, P1 V1 minus P2 V2. So now I need P2 by P1 ratio. I hope you do remember the heading of this topic. Prove that P2 by P1 is equal to. Understood? Here we need P2 by P1 ratio. So I will express this equation in terms of P2 by V1. So what I do, I will take P1 into specific volume common outside. So once you take outside, it will become 1 minus P2 by P1. Similarly, V2 by V1. I will take this is equation number 2. Now the steam flowing through the nozzle follows PV to the power of n is equal to constant, because in the topic itself he has given derive an expression for maximum discharge of nozzle for an isentropic flow. Isentropic is nothing but reversible adiabatic. So PV to the power gamma is equal to constant, or PV to the power n. So here at inlet I have written P1 V1 to the power of n. At outlet you apply the same equation, P2 V2 to the power of n. Now I will do some little bit mathematical correlations. Here V2 and V1 ratio I will take V2 by V1 to the power of n, and this P2 will go on the left hand side, P1 by P2. So power is nothing there. Okay, now you eliminate this n by multiplying 1 by n on both the side. Here also you multiply 1 by n, here also you multiply 1 by 1. So V2 by V1 is equal to P1 by P2 to the power of 1 by n. This is equation number 3. So now this equation number 3 you substitute here V2 by V1. I am replacing ratio of specific volumes by in terms of pressure. So now using equation number 3, the equation 2 becomes here C2 square by 2 as it is. This is equation number 2. Just see here, n by n minus 1 as it is, P1 V1 as it is, 1 minus as it is. So ratio of P2 by P1 as it is, into in place of V2 by V1 I will substitute this equation. So P1 by P2 to the power of 1 by n, and mathematical equations. So P2 by P1, again I need pressure ratio only in terms of P2 by P1. The ratio of P1 by P2, if you write P2 by P1, there will be sign conventions takes place. That is plus will become minus 1 by n. So you add these two power, n by n minus 1, P1 V1, 1 minus P2 by P1, add the power 1 minus 1 by n. Take the LCM. These three parameters are same. So 1 minus P2 by P1, take LCM. So once we take LCM, L is LCM, n minus 1 by n. On the left hand side, C2 square as it is. So divided by 2, you send to the right hand side, it will become 2n by n minus 1. Here again the step is same. Now C2 is equal to, because in the equation number 1, m is depends on C2. So C2 is equal to square root of the same equation I have written here. So I have taken equation number 4. Now from equation number 3, what is the equation number 3? 3 is we have taken P1 V1 to the power of n is equal to P2 V2 to the power of n. That is polytropic equation here. So using this equation, I will write V2 is equal to V1 P1 by P2 into 1 by n. V2 is equal to V1 P1 by P2 whole to the power of 1 by n. So this specific volume value at exit I will substitute in equation number 3. So from equation number 3, this equation again I have written one more time. So from equation number 4, equation number 4 is expression for velocity at exit of the nozzle, and equation number 5 is specific volume of steam at exit of the nozzle. Both these expressions you substitute in equation number 1. So equation number 1 I will show you here. We will go back to equation number 1. M2 or mass flow rate at exit of the nozzle is equal to A2. C2 divided by specific volume at outlet or exit of the nozzle. We have written expression for these two. Substitute here. A2 will be remain same. Here A2 as it is. A2 as it is. C2 is there. Write expression for C2. Just you copy from this here. 2 by n minus 1 P1. Nothing I have changed. Everything is same. Just I am substitute the expressions. So V2 in the denominator 2 V2 is there. So V2 is equal to here same equation I have written. Now left hand side is same mass flow rate. And dear students, now instead of writing in the denominator P1 by P2, if you take to the numerator, it will become P2 by P1. So A2 by V1 as it is. So this term I have taken on the numerator, it will become P2 by P1 to the power of 1 by n. So square root of, and remaining all terms are as it is, nothing changed. Okay, now so A2 by V1, here I have dotted with the 3 stars. So many students, when we go for valuation, we have seen some students will stuck here. Up to here they will derive and they will forget it what to write in the next step. So it is very simple. So A2 by V1 is as it is. Now you send this term ratio of P2 by P1 within the square root. So if you send it within the square root, it will become 1 by n, it will become 2 by n, because square root of 4, if you take outside, square root of 4 is 2, square root of 16 is 4. Similarly, so if you send 1 by n power ratio to inside the square root, it will become 2 by n. It is a mathematical rule, mathematical equations. So 2 into n by n minus 1 P1 V1 as it is. So this term I have taken here, and this term is as it is. I have taken 1 minus P2 by P1 n minus 1 by n. So this is one very important step you need to remember. So once you done this step, next one is easy. So A2 again as it is, nothing change in the equations with these parameters. This is also same, n by n minus 1 P1 V1. Now multiply ratio of P2 by P1 to the power of 2 by n with 1 as well as this term. So once you multiply here, the ratio is 1 into P2 by P1 to the power of 2 by n as it is. Now multiply these two, P2 by P1 2 by n, P2 by P1 n minus 1 by n. Okay. So A2 by V1 2 into n minus 1 as it is, P2 by P1 to the power of 2 by 1 as it is. Now add these two, because base is same, base is P2 by P1 is here, base is P2 by P1 is here. Okay, so the power we can add easily. So 2 by n plus n minus 1 by n. Okay, now mass flow rate exit, again some terms are copy as it is. Okay, here I take the LCM n, so it will become 2 plus n minus 1, that is n plus 1. LCM, we take LCM, n is LCM, n into 1 is n, so 2 plus n minus 1, so 2 minus 1 is 1 and n as it is. So I will take this is equation number 6. Okay, so from equation 6 you observe this equation 6 carefully. So in this equation number 6, that is mass flow rate of steam at exit of the nozzle depends only on one variable parameter, that is P2 by P1. Okay, have a look here. For A2 is geometric constant, it will be given in the problem or numericals. V1 is the specific volume of fluid at inlet. Inlet is, we can measure easily. Okay, 2 is constant, n is constant for the given gas, P1 is pressure at inlet is known value, because properties at inlet will be given and we can measure easily because it is in our hand. But the intermediate properties within the system we cannot measure. For example, velocity at exit we cannot measure. At in between the nozzles, velocity and pressure we cannot measure. So this mass flow rate of steam depends on only one independent parameter, P2 by P1. So I have written the same equation here. So it is a function of P2 by P1. And in mathematics you studied for maxima and minimum condition, differentiate with respect to independent variable and equate it to 0, you will get the maximum condition. I hope you remember, you are done in third semester and second semester, I think. Okay, so differentiate the equation number 6, that is mass flow rate, with respect to independent variable, you will get and equal to 0. So same equation number 6 I have written here. Here is the equation number 6, and P2 by P1 equal to 0. And here A2 is constant, send to the right hand side, it will become 0. V1 is also constant value, send on the right hand side, become 0. Square root of 2 is also constant, send on the right hand side, will become 0. N by n minus 1, similarly P1 by V1 also constant, send on the right hand side. So only remains these terms, ratio of P2 by P1 I have written as it is. And dear students, here I have differentiated this equation with respect to P2 by P1. So assume that this is x to the power of n. What is the differentiation of x to the power of n? N into x to the power of n minus 1. Here n is 2 by n, P2 by P1, x minus n minus 1. Same method you apply for this differentiation of x to the power of n. So n into x to the power of n minus 1. Okay, now you simplify. 2 by n, this term I will take left hand side, this minus terms I will send on the right hand side, so it will become easy for me to solve. So 2 by n, so this entire term I will send on the RHS, right hand side. So now once you send RHS, n get cancels. The remaining term I have written as it is, 2 by n plus 1. This n plus 1 I have taken on the left hand side, 2 and n plus 1 here, is equal to P2 by P1 n plus 1 by n minus 1. Take LCM, that is n is the LCM, n plus 1 minus n. So minus 2 by n, here I have substituted P2 by P1, take the LCM, n plus 1 minus n get cancels. So 2 by, you observe the first term and the last term. Here 2 is there, 2, n plus 1 I have taken on the left hand side, and this n get cancels here, 2 by n plus 1. So P2 by P1 to the power of 1 by n as it is. And here on the left hand side, the P2 by P1 to the power of 2 by n minus 1 I have taken on the denominator of the RHS. So if you take this term on the right hand side denominator or on right hand side, it will become sign change, plus will become minus, minus will become plus. So minus 2 by n plus 1. Base of these two parameters are same, and so that you can add the power. So add power, P2 by P1, 1 by n minus 2 by n plus 1. So take the LCM, so 1 minus 2 by n plus 1. So now, so this is 2 by n plus 1 is equal to P2 by P1 to the power of n minus 1 by n. So P2 by P1 is the critical pressure ratio I need. So P2 by P1 is equal to this. On the right hand side, you multiply with some power so that it get cancelled. So I will multiply with here n by n minus 1. I have written here, multiply by n minus 1 to both the side of the power. So P2 by P1 is equal to 2 by n plus 1. So P2 by P1 is equal to 2 by n plus 1 to the power of n by n minus 1. So what is the ratio of P2 by P1? That is called critical pressure ratio. So if they ask for Derive expression for condition for critical pressure ratio, up to here you have to derive. So this is for 12 marks or for 10 marks questions. So okay, in the next video lectures we will solve the numericals on steam nozzles. So to solve numericals we need steam tables and Muller chart diagram. Okay, thank you so much for watching this video.